Hey everyone, ready for a deep dive into something really cool?
I am.
We're talking Graph Convolutional Networks today.
GCN.
GCNs, yeah. They're changing how we look at data.
Especially when it's all about relationships.
Exactly. And we're going deep with this paper.
MixGCN. Scalable GCN training by mixture of parallelism and mixture of accelerators.
It's a mouthful,
That's a
but
good one.
it really is. So this paper is all about solving a big problem.
Huge problem.
Yeah. How do we train these GCNs on data sets that are massive?
Massive. Think like a network with over 100 million nodes.
Each with tons of information.
It's mind-boggling.
Makes a supercomputer sweat.
Absolutely.
Yeah.
It's not just about size, though.
What do you mean?
Well, it's a whole different way of thinking about machine learning.
Okay.
Traditional methods, they kind of struggle with data that isn't neatly organized.
Right.
But so much of the world is interconnected.
Yeah.
Think social networks, financial transactions even.
The way genes interact.
Exactly. GCNs let us capture those relationships. So it's a whole new level of understanding then.
It is.
Okay, I'm intrigued, but
Yeah.
let's back up a sec.
Yeah.
What does a GCN actually do?
All
Like imagine I've never even heard of a graph before.
right, challenge accepted.
No jargon allowed.
Okay, so picture a network
Okay.
where each point or node
Uh-huh.
represents something, like a research paper.
Okay.
And each paper has connections to others.
Like citations.
Exactly. A GCN lets each paper talk to its neighbors.
Oh.
It gathers information from them.
So it's like,
We call this neighbor aggregation.
okay.
And it helps each node understand its place in the network.
So each paper is like gossiping with the ones it's linked to
Exactly.
to get the inside scoop.
You got it.
I like that.
What happens next?
Well, once they've had their chat,
Ah.
each node uses that information to update its own understanding.
So kind of like refining its research based on what its citations are saying.
That's a great way to put it.
And that's the node update phase.
Precise.
Okay. And these two steps
Yeah.
help GCNs uncover all these hidden patterns and connections.
That's really cool.
It is.
So GCNs are awesome for analyzing real-world networks.
They are.
But this research is about tackling the really big data sets, right?
Yes.
The massive ones.
The problem is those giant feature tensors.
Okay.
So think about a data set like the one they mentioned, Ojbian papers 100M,
All right. Over 100 million research papers.
each with tons of features describing it.
Just storing all that data is a challenge,
Oh, absolutely.
let alone processing it.
Traditional computers just weren't designed for this scale.
So it's like trying to fit an elephant into a shoebox.
Pretty much.
So how do researchers usually try to solve this?
Well, they typically use something called partition parallelism.
Okay.
Basically, you split the data,
Okay.
that giant elephant,
Yeah.
into smaller chunks
Okay.
and give each chunk to a different computer.
So multiple shoeboxes.
Exactly.
Divide and conquer.
Right.
But I'm guessing there are downsides to this approach.
Definitely.
Like what?
Well, remember how GCNs work by nodes talking to their neighbors?
Yeah.
Well, imagine what happens when those neighbors are on different computers.
Oh.
You end up with a ton of communication overhead as they constantly share information.
That sounds like a logistical nightmare.
It is.
And I bet it's not always easy to split the data perfectly evenly.
You're exactly right.
Real-world graphs are irregular.
Very irregular,
So it's almost impossible to divide the workload perfectly between computers.
leading to inefficiencies and bottlenecks.
It's like trying to split a giant, irregularly shaped cake evenly between friends.
Yeah,
Someone's always going to feel a little cheated.
someone always does.
Okay, so where does MixGCN come in?
MixGCN.
This paper claims to have a more elegant solution.
It does.
What's their secret?
They call it mixture of parallelism, or MOP.
MOP. Okay.
So instead of splitting the data based on nodes and their connections, they split it based on features during that neighbor aggregation phase. So each computer handles a smaller, more manageable slice of information.
Hold on, I'm not sure I follow.
Okay.
How does splitting by features solve the communication bottleneck?
Right.
We still need all those nodes to talk to their neighbors.
Right.
Yeah.
That's where the mixture part comes in.
Okay.
So for the update phase, they switch back to node-level parallelism.
Oh, interesting.
This ensures each computer has all the information it needs
Yeah.
for its assigned nodes to update themselves based on the full conversation they've had with their neighbors.
So they found a way to balance focus processing with each node getting the full picture.
Exactly.
That's pretty clever.
It is a clever approach.
But what does that actually mean in terms of benefits?
Well, the benefits are substantial. First, no matter how many computers you add, the amount of data being moved between them stays the same.
Oh, okay.
This avoids that communication bottleneck.
So no matter how many people join the party, the noise level stays manageable.
Precisely.
I like
And plus, because the workload is balanced more effectively,
Yeah.
every computer stays busy and contributes equally.
So it's like a well-organized potluck where everyone brings a dish.
I like that analogy.
No one brings a dish so big it takes over the whole table.
Right.
And everyone contributes equally to a delicious meal.
Exactly.
That's a good analogy.
Thank you.
Okay, so MixGCN tackles data size with this MoP technique.
It does.
But we mentioned another challenge.
Yes.
Dealing with both sparse and dense operations.
Right.
What's that about?
Yes. The hybrid sparse-dense operations challenge.
Right.
That's where their second ingredient comes in. Mixture of accelerators.
Or MoWay.
MoWay, exactly.
Okay.
Now that they've smartly split the data with MoP, they can use different types of hardware for different parts of the task.
So the right tool for the right job.
You got it.
Okay, I'm intrigued.
All right.
What kinds of accelerators are we talking about?
So for the neighbor aggregation phase,
Okay.
which often involves sparse data structures, they propose using specialized sparse accelerators.
Okay.
These are designed to handle data where many of the connections between nodes are missing.
Sparse being the opposite of dense, where everything is connected to everything else.
You got it.
Okay.
And for the node update phase,
Yeah.
which involves a lot of number crunching,
Right.
they suggest using dense accelerators.
Which are more common.
Yeah, more common in systems designed for traditional deep learning.
So like having a team of specialized chefs in our potluck analogy,
I like where you're going with it.
each expert in preparing specific dishes.
A perfect analogy.
I
But they didn't stop there.
Really?
They found a way to make the process even more efficient.
Wow.
So they identified a unique sparse operation within GCN training and found a way to fuse two operations together,
Oh,
creating a shortcut.
it's like
Makes the whole process faster.
they're optimizing the recipe itself, not just the kitchen appliances.
Precisely.
I like it. What kind of performance gains are we talking about with all these improvements?
Their experiments show that mixed GCN can be up to 10.4 times faster than traditional approaches.
Seriously?
Yeah, and that's just the beginning.
Wow.
They believe mixed GCN has the potential to unlock even greater performance gains as hardware continues to evolve.
That's like comparing a horse and buggy to a bullet train.
It is quite a leap forward.
But I'm curious what's driving those speed-ups.
Okay.
Is it just raw processing power, or are there other factors at play?
It's a combination of factors,
Okay.
but one of the most important is memory efficiency.
Okay.
Remember how those giant feature tensors were a major bottleneck?
Yeah.
Well, mixed GCN's MoP technique significantly reduces the amount of memory needed to store and process those tensors.
So less memory usage means faster processing times.
Exactly.
That makes sense.
And the researchers compared mixed GCN's memory usage to other methods, and the results were quite striking.
Oh.
Mixed GCN consistently used less memory, and the difference became even more pronounced as they added more computers to the system.
So it's not just faster, it's also more memory efficient,
Yes,
which makes it even more scalable for truly massive data sets.
precisely.
What about communication overhead? Did they measure that as well?
They did.
Oh,
The
yeah.
results were just as impressive.
Really?
Mixed GCN maintains a constant communication volume regardless of how many computers are involved.
So
This is in stark contrast to traditional approaches.
where communication overhead increases as you add more machines.
Exactly.
Okay, so mixed GCN wins on speed, memory efficiency, and communication overhead.
It does seem to have it all.
It sounds like the perfect solution for GCN training.
It's a very promising approach.
But before we get too carried away, I want to hear more about those specialized sparse accelerators they mentioned.
Okay.
Tell me more about these SPUs
SPUs.
and why they're so important for mixed GCN's performance.
The SPUs are where things get really interesting from a hardware perspective. So remember how we talked about the neighbor aggregation phase being particularly well suited for sparse accelerators?
Yeah.
Well, the researchers actually designed and simulated a dedicated SPU specifically optimized for that part of the GCN training process.
So they didn't just use off-the-shelf hardware.
Yep.
They actually created their own specialized chip.
They did.
That's pretty impressive.
It is quite a feat.
And their design is based
For
on
really clever insights.
into the unique characteristics of GCN computations.
Exactly.
What?
Well, for example, they identified a specific operation called SPMM,
Okay.
which is a fusion of two common sparse operations.
Uh-huh.
And by designing their SPU to handle this operation directly,
Yeah.
they were able to achieve significant speedups.
Okay, I'm starting to understand why these SPUs are so crucial.
Yeah.
They're like custom-built engines designed to power through those sparse operations.
Very apt analogy.
But how do they actually compare to existing GCN accelerators?
Right.
Did the researchers provide any benchmarks?
They did.
And
They compared their SPU design to two state-of-the-art GCN accelerators,
okay.
high GCN and AWB GCN.
And
The results were quite compelling.
how so?
The mixed GCN SPU consistently outperformed both of those existing accelerators,
Wow.
achieving speedups of up to 3.4 times.
Okay, so not only is mixed GCN a game changer in terms of algorithms and system design,
Right.
but it also pushes the boundaries of hardware acceleration.
It really does.
It's like they've thought of everything.
They've covered a lot of ground.
But before we get too excited, I have to ask,
Sure.
are there any limitations to this approach?
That's a great question.
What are the potential downsides or challenges that researchers might encounter when trying to implement mixed GCN in the real world?
That's a very important consideration and one that the researchers themselves acknowledge in the paper.
Okay, good.
One potential limitation is the current need to duplicate the propagation matrix across all the accelerators involved in the neighbor aggregation phase.
So even with all of mixed GCN's memory optimizations,
Right.
there's still a potential for memory bottlenecks if you're dealing with truly massive graphs.
That's right.
Okay.
However,
Yeah.
the researchers point out that in most cases, the propagation matrix isn't the biggest memory hog. The intermediate embeddings and output logits,
Yeah.
which are already effectively handled by MOP, tend to consume far more memory.
So it's a potential concern, but not necessarily a showstopper for most practical applications.
That's right.
Okay, good.
And the researchers suggest some potential solutions for dealing with those extreme cases where the propagation matrix does become a bottleneck.
Oh, like what?
For example, they mention the possibility of combining MOP with traditional partition parallelism
Interesting.
to further distribute the memory load.
So even with its impressive capabilities,
Yeah.
mixed GCN isn't meant to be a one-size-fits-all solution.
It's not.
It seems like there's always room for improvement.
There always is.
But let's step back for a moment and talk about the bigger picture implications of mixed GCN.
Okay.
We've spent a lot of time discussing the technical details,
We have.
but I'm curious about the potential impact of this research
Yeah.
on the field of AI as a whole.
Right.
If mixed GCN can handle networks of this size,
Uh-huh.
what new possibilities does it unlock for understanding and analyzing the increasingly complex
Right.
and interconnected data of our world?
It's a fantastic question.
I'm talking about things like social networks,
Ah.
biological systems,
Yes.
financial markets, and so on.
That's a question that I think really gets to the heart of
Yeah.
why mixed GCN is so exciting.
It does, doesn't it?
Yeah. Yeah, it really does feel like we're on the verge of some major breakthroughs.
It seems like it, yeah.
We're not just talking about making GCNs faster.
Right.
We're talking about expanding the types of problems we can solve.
Give me an example.
Okay, so imagine analyzing the entire network of global financial transactions
Okay.
to detect fraud or even predict economic trends.
That would be incredible.
Or how about mapping the complex interactions between genes and proteins to develop personalized medical treatments?
The possibilities are pretty mind-blowing.
They are incredible.
And as we accumulate more and more data about the world,
Yeah,
the ability to analyze these complex networks,
becomes even more crucial.
it really does.
It does.
It's like we're finally getting the tools to understand the interconnectedness of
Yeah.
everything.
It's an exciting time.
But let's stay grounded for a moment.
Sure.
What are the next steps for these researchers?
Okay.
What challenges still need to be addressed?
Well, one area they highlighted is the need to extend mixed GCN
Okay.
to handle even more sophisticated GNN models.
Okay.
Right now, their method is primarily designed for simpler operations, common in many GCNs.
Right. But there are other types of GNNs that use more complex methods.
Exactly.
Like those graph attention networks I keep hearing about.
That's right.
Yeah.
The challenge is to figure out how to adapt their approach to handle those more complex methods without sacrificing its scalability and efficiency.
It's like taking our potluck to the next level
I like that.
with dishes that require more intricate techniques
Yeah.
and coordination.
I agree.
I'm sure they are up to the challenge.
I think so too.
But what about the hardware side of things?
Okay.
Those SPUs seem like a crucial piece of the puzzle,
Yeah.
but are they really feasible to implement on a large scale?
That's a valid concern.
Yeah.
The good news is that the researchers have done their homework.
Okay, that's good.
They've provided detailed simulations and power consumption analyses of their SPU design.
So it's not just a theoretical concept.
Yeah.
It's something that could actually be built and used.
That's the idea.
And as technology advances,
Yeah.
it becomes increasingly feasible to create custom hardware tailored for specific tasks,
Absolutely.
like those found in GCN training.
That's right.
So we're talking about a future where AI systems are powered by a mix of general-purpose processors and specialized accelerators,
Yep.
each optimized for a different part of the machine learning process.
Precisely.
That kind of heterogeneous computing is likely to become more and more common
I think so.
as we push the boundaries of AI.
Absolutely.
This has been an incredibly insightful deep dive into the world of GCNs.
It has.
It's amazing to see the work being done to make them faster, more efficient, and more scalable than ever before.
I agree. It's a very exciting time to be following this field.
It really is.
Yeah.
Yeah.
It really is a fascinating area of research.
Absolutely. And it's great to see how these researchers are pushing the boundaries.
It is.
So to wrap things up,
Okay.
I want to leave our listeners with something to think about.
All right.
If MixGCN can handle networks of this size,
Uh-huh.
what new possibilities does it unlock for understanding our increasingly complex
Yeah.
and interconnected world?
That's the big question, isn't it?
It is.
What can we do with this new power?
Exactly.
It's a bit daunting, but mostly exciting. I think.
Agree.
There's so many potential applications.
Like you were saying earlier.
Yeah, like analyzing those financial transactions.
Right. Or mapping the interactions between genes
Uh-huh.
to develop new medical treatments.
It's incredible to think about.
It really is.
It's like we're on the cusp of a new era of understanding.
Maybe even a new era of AI.
Possibly, yeah.
And MixGCN is helping to lead the way.
It's definitely a major step forward.
So until next time,
Yes.
stay curious, everyone.